This presentation is delivered by the Stanford Center for Professional Development.
All right, today I want to continue down the path that we started last time of talking about general properties of the Fourier transform. Remember, as I've said now a couple times, there are two tracks that we're following in developing our understanding techniques of using the Fourier transform. One is to develop specific transforms of specific functions that you need to have sort of at your fingertips, so to speak, the kind of things that come up often enough that you want to know what the answers are, what the formulas are. And the second path is to understand how to take the Fourier transform of different combinations of functions, different combinations of signals that again come up often. So that's what we're going to do today. We're going down more the second path, including an extremely important operation. So we're going to have three big items today, each of which are important in themselves and come up all the time. One is delays, what to do with the Fourier transform of when a signal is delayed. One, a formula for what happens to the Fourier transform under a stretch, stretches. And finally, a very general operation, which we have now seen a couple times in different forms, but today we're going to see it in the context of the Fourier transform in its full glory, so to speak, and that is convolution. Okay? So I want to take each one of these in turn, and I want to derive what the formulas are for you. The book has, or the notes have examples of how they're used in practice, and you'll also have plenty of chance to practice some of these in problems. What I want to do is show you what the general formula looks like and how it comes about. All right, so let's first look at the question of delay, and there the question is, if a signal is delayed by, or in the same term, I'm not sure which term you prefer. I'm not even sure which term I prefer. Delayed or shifted. Say shifted by an amount b. What happens to the Fourier transform? All right. In other words, if the signal is f of t, and that corresponds to a Fourier transform capital F of s, so I'm going to use the capital notation here, then if a signal is delayed by an amount b, and for the purposes of this discussion, that means I consider f of t minus b, not f of t plus b. And again, it's always a question of what you mean by delay, whether you take a plus or minus, but I think this is probably a fairly standard way of looking at it. Then the question is, what happens over here? What happens to the Fourier transform? All right, now this is the sort of question that you have to be able to answer for yourself routinely. These are very simple cases, but there are other cases where similar sorts of things come up, not too many, fortunately. And again, we have no recourse here other than to deal with the definition of the Fourier transform. All right, so the Fourier transform of f, or I suppose I should write it with a capital F, since I started with that notation. So capital F of s is the integral from minus infinity to infinity, e to the minus 2 pi I st f of t dt. And then the Fourier transform of the signal f of t minus b is the integral from minus infinity to infinity, e to the minus 2 pi I st f of t minus b dt. All right? Now, when you get enough experience, and by now you probably have that experience, when you look at something like this, the thing that cries out to be done here is a change of variable. You want this to look as much as possible like the ordinary formula for the Fourier transform. That means f of a single variable here rather than f composed with anything. So what you do is, the simplest thing is to make a change of variable, say u equals t minus b. B is a constant, so du is equal to dt. And t is equal to u plus b then. And if the integral goes from, if t goes from minus infinity to infinity, since I'm just subtracting off a fixed constant, so does u. So in terms of the new variable, the integral becomes the integral from minus infinity to infinity, e to the minus 2 pi I s. T becomes u plus b. And f becomes f of u, the function becomes f of u du in terms of the new variable. Okay? And now the thing that's crying out here is to manipulate the complex exponential. So write that as the integral from minus infinity to infinity, e to the minus 2 pi I s u times e to the minus 2 pi I s times b f of u du, and realize that because I'm integrating with respect to u, this term does not, this second complex exponential here, e to the minus 2 pi sb, does not depend on u, so it comes out of the integral. It's a constant as far as integration is concerned. So I can write that as e to the minus 2 pi I sb, integral from minus infinity to infinity, e to the minus 2 pi I su, f of u du, and what remains is the complex exponential, this complex exponential here, times the Fourier transform of f, the original Fourier transform, the Fourier transform of the original function f. That is, this is e to the minus 2 pi I sb, f of s, what I call capital F of s. Okay? So where do we start? Where do we finish? We started by shifting f, and we discovered what happened to the Fourier transform. In other words, I'll do it over here to finish my arrows. That if the original signal f of s has Fourier transform, little f of t, excuse me, has Fourier transform capital F of s, then the Fourier transform of f of t minus b corresponds to e to the minus 2 pi I sb capital F of s. All right? Now, so that was a very simple derivation. This is sometimes called the shift theorem, delay theorem. People call it various things. It's very simple, and it comes up all the time. And for me, actually, you know, I have sometimes trouble remembering whether it's a plus or minus up here. All right? So that's my own personal burden. So it's actually maybe worthwhile to write down, in general, f of t. If I changed a plus to a minus, the minus to a plus here, I'd have a plus here. So I even usually write down the formula that looks like this. The Fourier transform of f of t plus or minus b corresponds to e to the plus or minus 2 pi I sb capital F of s. Okay? Same formula. I mean, I haven't done anything different, but sometimes I like to remember them sort of distinctly, but that's my own burden. This is an example, actually, where the notation can be a little bit of a problem, all right? That is, in this case, sort of the uppercase notation is probably most helpful, indicating how the signal is paired with its Fourier transform. And if you change the signal, how does that change the Fourier transform? Because writing down with the operator notation, writing this down is kind of awkward because f is already evaluated at t minus b. You take the Fourier transform, that's supposed to be evaluated at another variable. What do I write like this? Do I write this evaluated at s? I mean, it's just, that's okay, but that's a notation only a mother would love. You know, I mean, it's just too complicated. All right, so, you know, we can all understand sort of by ladies and gentlemen's agreement what you mean when you write down the Fourier transform of f of t minus b. But all I'm saying is that you have to be very careful with your variables and how you write them, what you don't write. And if you don't believe me, you'll have plenty of occasions to screw it up, trust me, all right, because everybody does. It's just in the nature of the subject that the notation can sometimes be, like I say, there's a certain ambiguity in the notation. It can sometimes cause problems, all right? So this is sort of a bad notation. In that case, although I don't usually like to use it, it's probably a better notation. All right, so the formula itself is very simple. What is the interpretation of the formula? The interpretation is also something to keep in mind. Interpretation. And that is a shift in time corresponds to a phase shift in frequency. So here I think it's actually better to use the word shift instead of delay because I can use it in both sides of the sentence. Shift in time corresponds to a shift in frequency, but a shift in frequency you think of as a phase shift. Corresponds to a phase shift in frequency. If I think of the signal as living in the time domain and its Fourier transform as living in the frequency domain, phase shift in frequency. So why do I say this? Well, because what I have in mind with a statement like that is that the Fourier transform is a complex number, all right? So it has a magnitude and it has a phase. So I write f of s, the Fourier transform of the original signal, as its magnitude, the magnitude of f of s, that's a real number, times e to the 2 pi I, say, theta of s. So theta is the phase. And then if I multiply Say this is not a hard thing, but it's a thing you have to sort of, again, keep in your head. Not only the formula, but in the interpretation of the formula. So e to the 2 pi, or e to the minus 2 pi, SB times the Fourier transform of S is, the magnitude stays the same. And it's this complex exponential times that complex exponential. So that's e to the 2 pi I theta of S minus 2 pi I S theta of S minus B. I have an S in both cases. No, I don't. 2 pi I theta of S minus SB. Okay? In general, the phase can depend on S. That's why I write a theta of S. All right? The phase can vary with S as well. It usually will. Okay? So there's the phase shift. Here's the magnitude is the same. The magnitude of the spectrum does not change. The magnitude of the Fourier transform does not change. All right? What changes is the angle. So I will let you push that interpretation however far you want, but that is if you want to think about other sorts of ways. But that's the basic interpretation of the shift theorem. A shift in time corresponds to a phase shift of the frequency, in the frequency. And the magnitude stays the same. So again, I will sort of let you convince yourself that that makes sense sort of on physical, intuitive grounds if you think about a signal and how it's made up. All right? Okay. Next, these things are not, I mean, I like these formulas, and I think that it's nice the way these formulas work out. This is not as exciting as some of the other things we've done, I admit. All right? But nevertheless, it's sort of part of the whole package that you have to be familiar with, you have to be comfortable with. And it's not only the formulas, it's how the formulas are derived. One of the reasons why I'm going through this is just to show you, and so I hope you can also show yourself, is just the kind of techniques that are involved in deriving these formulas. All right? Because if you can see them in these relatively simple circumstances, often it's the case that you can apply them in more or less the same way in slightly less obvious or less simple circumstances. It's a pedagogical kind of thing. All right. Now, the second general theorem is what happens when, or formula is what happens when you scale the time. And here actually there's a very important interpretation that I'll talk about after we get the formula. All right, but this one I think is a deeper property, reveals a deeper property of the Fourier transform. Scaling is scaled, but when I say scaling, I'm talking about scaling the independent variable, scaling the time. Scale, if f of t again corresponds to, let me just write it like this, a Fourier transform capital F of S, then if I scale the time by a constant a, so I'm thinking of a as just a real number here, but not necessarily positive, then what happens to the Fourier transform? Okay? All right, so again, to answer this question, we have no recourse other than to turn to the definition. So the Fourier transform of the scaled version of f is the integral from minus infinity to infinity of e to the minus 2 pi I st f of at dt. And again, the thing that is crying out to be done here is a change of variable. But it's helpful, I think, to make a distinction here whether a is positive or negative because of what happens when you make that change of variable to the limits. You know, we have a variable of a definite integral. The limits of integration also have to change. And it's helpful here to make a distinction. They change differently whether a is positive or negative. So let's take the case when a is positive first. So if a is positive, I'm going to in either case, positive or negative, I'm going to make the change of variable du equals a times dt. That's clear that I want to do that. Then, of course, du is equal to a times dt. All right? Now, if a is positive and t goes from minus infinity to infinity, then so does u. U also goes from minus infinity to infinity because a is just a fixed constant here. So the integral becomes the integral from minus infinity to infinity of e to the minus 2 pi I s u over a times f of u, dt becomes 1 over a times du. Okay? And the a is a constant, I can factor that out of the integral. The integral is from minus infinity to infinity. And this is minus 2 pi I. I'm going to put the 1 over a with the s instead of the u. And if I do that, why, it's plain enough what you see. what remains is the Fourier transform of the original signal f evaluated not at s but at s over a. Okay? So this is, I'll do it over here. So that is 1 over a times the Fourier transform of the original function, not evaluated at s, but evaluated at s over a. Fine. Done. Very nice. Very good. Okay? Now, what about if a is negative? If a is negative, let's take that case. So again, I'm going to make the same change of variable. Du equals a times dt. Du is equal to a times dt. Formally, that's all the same. All right? Now, what happens to the integral? The integral becomes, so here you have to be a little more careful. If a is negative and t goes from minus infinity to infinity, then a times t goes from plus infinity to minus infinity. All right? Some people are skittish when I write integrals. Like they say, you can't do that. You can't write an integral from a bigger number to a smaller number. And I say, I just did. You know, nothing happened. God did not strike me dead yet. All right? So you just have to be careful. So it's the integral from plus infinity to minus infinity, and then the rest of the integral looks the same formally. That is minus 2 pi I s u over a f of u, and then dt becomes 1 over a times du. All right? So that now, I got to start to use all three of my boards, you know, getting a little silly here. So the 1 over a comes out of the integral. I'll do this in two steps. So it's 1 over a, the integral from plus infinity to minus infinity of e to the minus 2 pi I, and again I'll bring the 1 over a to the s instead of the u, f of u du. And now if I want to recognize this as a Fourier transform, I swap the limits of integration. Instead of integrating from plus infinity to minus infinity, I integrate from minus infinity to plus infinity, but then of course I have to change the sign. So this is minus 1 over a times the integral from minus infinity to infinity of e to the minus 2 pi I s over a u f of u du, which is minus 1 over a times the Fourier transform evaluated at s over a. So it's, which is, write it down to finish it up, minus 1 over a times the Fourier transform of the original signal evaluated at s over a. Now, you can combine these two. So that's how the two formulas look. And they're different, sort of, when a is positive and when a is negative. But really, you can write the formula, you can combine both cases. If you realize that if a is negative, minus a is positive. In other words, this is the same thing as 1 over the absolute value of a times the Fourier transform of s of a. The Fourier transform of the original function signal as signal of f, the Fourier transform of the original signal evaluated at s over a. All right? And of course, this also includes the previous formula, because if a is positive, taking the absolute value doesn't do anything to it. It just returns the original value. In other words, the stretch theorem or the similarity theorem, whatever term you want to use, can be written in one piece. I had to do the derivation really in two parts, all right? But there's only one formula. And the formula is that if f of t corresponds to f of s, then f of at corresponds to 1 over absolute value of a times the Fourier transform of the original signal at s over a. So notice the absolute value is on the outside here, but not on the inside, okay? Now, I suppose you should say something like, you know, of course, a is not 0. But, you know, I take triviality insurance out on all my statements, all right? If my statements are trivially true or trivially false, you can ignore them, because I know I will, all right? Okay, that's sometimes called the stretch theorem or the similarity theorem, because the scaling is either called a stretch or a similarity. Similarity is probably a better term, because stretching and shrinking can be sort of the same sort of operation depending on whether or not a is bigger than 1 or a is less than 1. And let's talk about that point. All right, what is the interpretation of this? Because this actually has, I think, a more, fundamental interpretation than the stretch theorem. All right, what is the interpretation? All right? Well, let's take the case, first of all, when, say, a is bigger than 1. So I'm going to just consider a positive here. So I'll take a to be positive. All right? And then first, take a bigger than 1. If a is equal to 1, I'm not doing anything, of course. If a is bigger than 1, then how does, say, the function f of at compare with the function f of t? Or the graph of the function f of at compare with the graph of the function f of t? So how does f of at compare with f of t? Well, if a is bigger than 1, then roughly, and there's, you've seen this, you saw this like back in 8th grade when you were first learning these things, but it's sometimes, I always have to tell myself, I always have to give myself an argument for how these things look like. So if the signal is sort of like this, all right, if this is f of t, then f of at is the same signal except it's squashed. All right, it is compressed. Same shape, more or less, but sort of a squashed version. F of a, I can't draw this very well. F of at is a compressed form of version of f of t. You convince yourself of that if the variable is bigger, if I scale by something bigger than 1, then I'm squeezing the function. All right? What about the Fourier transform? What happens on the Fourier transform side? On the Fourier transform side, originally I had the Fourier transform of s, and then I go to the Fourier, if I change the, if I scale it, I go to 1 over a f of s over a. Now, I'm going to draw the graph, but the graph is a little bit deceptive here because you can't draw the graph of the Fourier transform because the Fourier transform is complex valued. All right, so people make this slip all the time where they think they're going to draw a picture of the Fourier transform, but you can't really draw a picture of the Fourier transform because you'd be plotting complex numbers. So what people actually plot when they plot pictures of the Fourier transform is its magnitude. Okay? So what about, so when I draw a picture here, make that realization. So if this is the original Fourier transform, if the signal is real, the Fourier transform is going to be, the magnitude of the Fourier transform is going to be symmetric. So it's going to look something like this. Looks a lot like that, actually, but that's just because I have lack of imagination when I draw my functions. All right, so if this is f of s, or rather say the magnitude of f of s, all right, then if I scale here, what happens? All right, if a is bigger than 1, s over a is less than, 1 over a is less than 1. All right, so I am multiplying, I'm scaling s by something less than 1. If I scale by something less than 1, I'm stretching the graph out instead of compressing it. And I'm also multiplying by something less than 1 out front. So that there's actually a stretching in the horizontal direction and a shrinking in the vertical direction. And again, this is not so easy for me to draw, but it's like a stretched out version of the signal. And shrunk. So it's stretched out horizontally. So this is 1 over a, I don't have to put the absolute value there because I'm assuming it's positive, 1 over a f of s over a, magnitude. So it's stretched out horizontally, and it's also squeezed down vertically. I don't know what to say. Stretched and squeezed vertically, and decreased, squeezed vertically. Is that right? I don't know. How do I say that? Decreased vertically. Squashed. All right, that's the technical term. Squashed vertically. Okay? Okay, and so that's what happens if a is bigger than 1. If a is less than 1, the situation is reversed. Okay? If a is less than 1, if a is less than 1, then if this is f of t, then f of at is stretched out. Yeah, like that, okay? Stretched out. And what happens to the Fourier transform? That is squeezed together. Because again, the Fourier transform is then scaled by something bigger than 1. So again, the Fourier transform goes to, the original Fourier transform goes to 1 over f, so value of a is positive, 1 over a, f of s over a. But again here, if a is less than 1, 1 over a is bigger than 1, so the Fourier transform is squeezed. So if this is the original Fourier transform, so to speak, absolute value of f of s, then 1 over a is going to stretch things in the vertical direction because 1 over a is bigger than 1. And it's going to squeeze things down, so maybe something like that. Okay? So it's squeezed and not squashed, unsquashed. Squeezed and stretched. I think I won't write that down. Okay, now, think of the extreme cases here. Think as a is getting bigger and bigger, greater than 1, greater and greater than 1, or if a is getting less and less than 1. What does it mean? Let's take the case when a is bigger than 1, all right? Much bigger than 1. You're getting larger and larger. If a is getting larger and larger, then the signal is getting more and more compressed. All right? It is getting more and more localized in time. All right? On the other hand, what is happening to the Fourier transform? If a is getting larger and larger, the Fourier transform is getting more and more stretched out, and that, for that matter, also squeezed down in the vertical direction. All right? This is an example, an extremely important example, of this sort of reciprocal relationship, and I use that term so pretty broadly here. I mean, you see reciprocals coming in, all right, but sort of in words and in feeling. You can't have a signal which is both localized in time and localized in frequency. All right? To localize this signal in time would be to squeeze it down, like look at the scaling of this, f of at for a very large a. All right? But that has a consequence in frequency of stretching things out. All right? So if you want to concentrate the signal in time, the Fourier transform is going to stretch out. And the reverse situation also holds. If you take a signal and stretch it out in time, by scaling by a number less than 1, scale by 1/10th, by 1/100th, by 1,000th, whatever, then you are stretching it out in time, but you're concentrating it in frequency. All right? The Fourier transform is getting squeezed. All right? That's an extremely that's a very important and a fundamental property of Fourier transforms, of the picture in the signal, of the signal in the time domain and in the frequency domain. And it comes up all the time. And it's a very important piece of intuition for you to have. All right, so you cannot have, and that's, to me, that's somehow the most important consequence of the stretch theorem. This theorem is what it says about localizing the signal in time versus localizing the signal in frequency. All right, you can't have, a signal cannot be both localized in time and in frequency. Now, this is one instance of this. There are other instances, actually. There are other ways of writing down that sort of relationship, all right, of translating this sentence into more precise mathematical terminology. One of the most famous ways, which I'm not going to do, it's actually in the notes, one of the most famous ways of translating this is the Heisenberg uncertainty principle, all right? That you can't localize a particle both in space and in time, right? You can't know both its velocity and its position to arbitrary precision. That actually that can be analyzed. Heisenberg uncertainty principle, and God knows I know nothing about it, can be proved, and there's a derivation in the notes actually, by techniques of the Fourier transform, by using the Fourier transform, and it essentially comes down to this fact that the Fourier transform that a signal cannot be both localized in time and in frequency. That if you stretch out in one domain, you're going to squeeze in the other domain, and vice versa. Okay? Now, so this is a very important point of intuition for you. Now, one interesting thing, if you think about what we showed about the Gaussian, all right? We showed, as a remarkable fact, that the Fourier transform of the Gaussian is itself. So recall the situation with the Gaussian. F of t equals e to the minus pi t squared. When it's normalized this way, then the Fourier transform is, again, is the same thing. F of s equals e to the minus pi s squared. Same thing. All right? So from this, interpreting the Gaussian or putting this interpretation onto the Gaussian, you might say, the Gaussian is perfectly balanced somehow in both time and frequency. It is It is what it is. I mean, it is perfectly balanced, all right? It's just concentrated enough and just in time and just concentrated enough in frequency, or just spread out enough in time and just spread out enough in frequency. So it's the same thing. Taking the Fourier transform doesn't change it. Pretty cool, actually. Pretty cool. So it's perfectly balanced. I mean, I don't know how better to say this, but you sort of get the point, I hope. Perfectly balanced in time and frequency. Okay? All right. So these things are in general use now and everyday use. You're going to use these things all the time. People who work in signal processing can just whip these formulas out without any problem, and they are quite familiar with these interpretations. The formula that I won't write down for you, but is in the notes, and there's some examples of it, and I think there's some problems of it, are what happens when you combine shifts and stretches. All right. The formulas get a little uglier. The formulas, but you can. It's not there's nothing new involved in that, but it's just a question of combining the formulas in the right way. And part of it actually is a question of the variables and how you understand parentheses and everything else. So I'm not going to write down that formula, because unless I practice it a couple times, I'll get it wrong. But that's the one sort of formula in this general circle of ideas that also comes in, is the formula for the Fourier transform when you both stretch and delay. So like f of at plus b, something like that. All right, so I'll let you struggle with that quietly. Talk it over dinner. Right. All right, so one more. Go out with a bang today. And that is to introduce the idea of convolution. Again, something that you've probably seen in other classes, something that we've already seen in the context of Fourier series, but now we want to see convolution in the context of Fourier transforms and the way that it arises in the context of Fourier transforms, which is different, most naturally different than the way we saw it first coming up in the context of Fourier series. There we saw it in the context of solving differential equations, and that same interpretation, or that same use of convolution again comes up, but that's not the way it's motivated, all right? And that's not the way that's not the most fundamental role it plays, at least for questions of signal processing. So convolution is probably, I think it's probably safe to say, it's probably the most important operation in signal processing. I think that may be a little bit of an exaggeration, but not too much, all right? So I'll say probably. Most frequently used, most flexible, important operation in signal processing. Now, what is signal processing, since I've used that phrase, or what's the fundamental question of signal processing? Signal processing very broadly can be said to, you might define it as saying, how can you use one function to modify another? How can you use one signal to modify another? All right? That's the basic question of all signal processing. I mean, don't lose sight of this. Is how to use one function to modify another. Or one signal. All right, now, you can ask this question, or you can take this approach in either the time domain or the frequency domain. And again, it's equivalent, because if we can go from one to the other by the Fourier transform, or the inverse Fourier transform. I'd say it's probably more common to address this question in the frequency domain. That is to say, when you talk about modifying a signal, most often, not always, but most often you're talking about modifying the spectrum of the signal. All right, so most often you look to modifying the spectrum of a signal. And then at the end of the day, so what it is, you take the Fourier transform, you screw around with the spectrum, that's the technical term for it, and then you take the inverse Fourier transform and you have modified your original signal somehow. But the operations you perform are often conceived of and carried out in the frequency domain, and then you go back and forth between the two domains again by the Fourier transform or the inverse Fourier transform. Now, there's a very simple example of this. For instance, linearity actually gives you, in some sense, that's the simplest example of signal processing, or simplest operation in signal processing. So e.g., linearity or superposition. That is, the Fourier transform of f plus g is the Fourier transform of f plus the Fourier transform of g. All right? So think about f as the signal that you want to modify. Think of the signal g as the one that's doing the modifying. You don't like the spectrum of f, fine, add something to it that takes away a little bit here, takes away a little bit there, adds a little here, adds a little there, and then go back. All right? So you modify ff, the frequency, the spectrum of f, by adding the spectrum of g. You don't know what g is, say, but then you can take its inverse Fourier transform and find out the function that does the modifying for you. Right? Usually think of linearity as the sort of simplest property of Fourier transforms. It follows from the linearity of the integral. The integral of the sum is the sum of the integrals, right? And you don't think it's really worth commenting on. But in some sense, it's the simplest and most basic operation of signal processing. You don't like the spectrum? Add something to it. All right? All right, viewed in that light, and of course I can also scale by a constant. That's even less interesting in some sense. That's the other part of linearity, is I can just multiply by a constant here. But anyway, viewed in this light, a very natural question is, what if I want to multiply? So what about multiplying? That is to say, on the frequency side, I have my original function f, and I want to multiply it by the Fourier transform of another function g. So I'm scaling each individual frequency, so to speak, each individual point in the spectrum by some function g that I want to construct that does what I want it to do. And the question is, how does that come about? That is there some combination of f and g in the time domain so that in the frequency domain, so that in the spectrums multiply? All right? The spectrum of f is multiplied by the spectrum of g. The values of the Fourier transform of f are multiplied by the values of the Fourier transform of g. Can I do that? Is this f of some f combined in some unnatural way with g? That's the mystery. Can I find a way of combining f and g so that the sequence of the Fourier transforms multiply? All right? Not so unnatural. Not so unnatural. All right. So to answer this question, we're going to adopt a now familiar strategy. You've heard me say many times, this is how mathematics gets applied. Suppose the problem's solved and see what has to happen. All right? So suppose the problem is solved. Now I want to be careful. I want to look at my notes because I want to use the same variables that I use in my notes so I don't confuse the issue if you go back and forth between what I'm saying in class and what I say in the notes. Okay? So give me just a second here. So I say I want to suppose the problem's solved. So suppose I look at the Fourier transform of g at s times the Fourier transform of f at s. All right, and I just play with this. What happens if you multiply the two spectrum? Well, the Fourier transform of g is the integral from minus infinity to infinity. I have no recourse here but to go to the definition. Minus infinity to infinity, e to the minus 2 pi I, and here's where again I want to look at my notes. S of t, st, g of t, dt. And the Fourier transform of f at s is the integral from minus infinity to infinity. And here I want to write this. I already used t, integrating with respect to t. And so I want to integrate with respect to another variable, and you'll see y in just a second. E to the minus 2 pi I s x f of x dx. All right, I think I can take it from here. That's all I wanted to check. All right, now, watch this. All right, this is the product of two single integrals. They are decoupled, so to speak. All right, so that is I can write this as one big double integral. E to the minus 2 pi, I won't do that. I don't want to skip too many steps here. E to the minus 2 pi I st, e to the minus 2 pi I sx, g of t, f of x, dt dx. Okay? There should be no problem. You should be able to see that. And if you're having trouble seeing it, instead of going from here to here, imagine yourself going from here to here. All right? The variables are decoupled. When I say the variables are decoupled here, I mean they're decoupled. I don't know how else to say it. All right? There's no relationship between the variables. Everything happens independently. Okay? Now, combine the complex exponentials. combine the complex exponentials. That is, write this integral from minus infinity to infinity, integral from minus infinity to infinity. By the way, there are issues here. I mean, you know, there are things about turning. I'm going to swap limits of integration. I'm going to swap dt, dx, dx, dt, all the rest of that stuff. As I've said before, the rigor police are still blessedly off duty. All right, so this is e to the minus 2 pi I. I have a common factor of s in both exponentials, and I get an t plus x. Right? G of t, f of x, dt dx. Okay. All right, now, I haven't done anything there except algebraically combine the two exponentials. All right, now I want to do something a little trickier. I'm going to write this double integral as iterated single integrals. All right, so now the variables are coupled, really. So I'm going to write this as the integral from minus infinity to infinity. The inside integral, integral from minus infinity to infinity, e to the minus 2 pi I s t plus x, g of t, dt, and then the result is integrated against f of x dx. Now let's check to make sure that everything's okay here. That is, I actually get a number at the end of the day. On the inside integral, I have a function. This kernel here involves both, well, s, t, and x, all right? I'm integrating with respect to t, so what remains is a function of x. Forget about the s. That comes out sort of in the end. But think about this as a function of t and x because those are my variables of integration. So if I integrate this with respect to t, this inside integral, what remains is something that depends on x. I multiply that by f of x. I integrate with respect to x. I'm done. Everything's okay. So the only thing that remains here is a function of s, and that's the product of the Fourier transforms. That's what you expect. Okay? All right. Now, once again, what this calls for, if you can only hear it calling, so I'm training your ears and your eyes, is a change of variable. All right? So I'm going to let u equal t plus x. So du is equal to dt. See, the inside integral is with respect to t, so that's the variable here. Du is equal to dt, and then t is equal to u minus x. All right? So what happens to the inside integral? And again, if t goes from minus infinity to infinity, then so does, for any fixed x, so does u go from minus infinity to infinity. So I get the integral from minus infinity to infinity of the integral from minus infinity to infinity of e to the minus 2 pi I s t plus x is u, g of t, which is u minus x, du, then integrate with respect to x, f of x dx. Okay? Cool. May seem pointless, but it's not. All right, now I'm going to swap the order of integration. Instead of integrating du dx, I'm going to integrate dx du. And I'm going to write this as the integral from minus infinity to infinity. The inside integral becomes the integral from minus infinity to infinity of g of u minus x, watch, f of x, I'm skipping a step here a little bit, but not much, times e to the minus 2 pi I su du. All right, is everything okay there? Let's check. I skipped a step here. I sort of put everything together. I could have taken one more step and put everything together and then pulled it apart. So I have, again, into two iterated single integrals. This integral with respect to x, and then what remains, again, I integrate this with respect to x. What remains is a function of u. I integrate that against this kernel, this complex exponential, e to the minus 2 pi I su. With respect to u, what remains is a function of s. Want me to say that again? No. All right, so I skipped a step there. I took that iterated integral. I could have written everything together, grouped everything together, and then split it up again into two iterated integrals. All right, now look. Say we have eyes if only we but see. This integral inside here is a combination of u and of g and f, and it is getting integrated against a complex exponential. That is, if I now am so bright, am so far-sighted, if I am so damn brilliant, I will now realize that I have solved my problem. All right? I'm going to define h of x, h of u, I guess it is, to be the integral, I'm going to get my variable straight here. Yeah, h of u to be the integral from minus infinity to infinity of g of x minus u, f of u, no, u minus x, f of x dx, right? That's what I have in the inside integral. U minus x, yeah, f of x dx. And then what I have is the integral from minus infinity to infinity of e to the minus 2 pi I su h of u du, which is the Fourier transform of h evaluated at s. Now, once again, where do we start? Where do we finish? All right? Where do we start? Where do we finish? I discovered that the Fourier transform of g at s times the Fourier transform of f at s, too many parentheses here, Fourier transform of g at s and Fourier transform of f at s is the Fourier transform of h at s. The spectrums multiply if I define h by this formula. If we define h of u equals the integral from minus infinity to infinity of, where is it there? There it is, g of u minus x, f of x dx. Okay? I solved my problem. Once again, what was the problem? I said, is there a way of combining f and g so that in the time domain, so that in the frequency domain, the spectrums multiply, the Fourier transforms multiply? And the answer is, yes, there is, by this complicated integral. All right? It's not so obvious, right? This is not the first thing you wouldn't get out of bed in the morning and write this down, right, and expect that this was going to solve that problem. How do we get it? He said, suppose the problem is solved, see what has to happen, and then what you have to recognize is when it's time to declare victory. All right? And it's time to declare victory. All right, now, being an obnoxious mathematician, you cover your tracks and say, well, I'm simply going to define the convolution of two functions by this formula. All right? Let me use a different variable here to write the definition down. So now I'm going to define. That's how mathematics works. You turn the solution of a problem into a definition. It irritates the hell out of some people, but that's how it works. So define the convolution of f and g by this formula. Say, and the special notation is used g star f. Let me call the variable x here. All right. So it's the integral from minus infinity to infinity g of x minus y f of y dy. All right. Define the convolution of that. And then if you're a mathematician, you'd say, well, sure, I defined that. That's what could be more natural. And then you prove the theorem. Then you prove separately that you prove this remarkable fact that the Fourier transform of the convolution is the product of the Fourier transforms. But what's missing in that derivation is the game is rigged. You know, I mean, this definition was come upon precisely so it would satisfy that property, so that the Fourier transform multiplied the two signals. So the Fourier transforms multiply. Okay, then we have the Fourier transform of the convolution g star f is the Fourier transform of g times the Fourier transform of f. Remarkable. Remarkable, but I said the game is rigged. I mean, I set out to solve that problem, and I solved that problem, and then I sort of covered my tracks by saying, well, define the convolution by this, and then we have the remarkable convolution theorem that the Fourier transform of the convolution is the product of the Fourier transforms. But of course you do, because you set it up that way. All right? Now, I don't want it to seem like we have done something insignificant here. We've done something extremely significant, all right? Because the idea of being able to modify a signal by multiplying the Fourier transforms is a very powerful thing to be able to do. And what this says is there is a way of combining the signals in the time domain by a not so very obvious thing. It's a nice enough looking formula, sort of an elegant looking formula, but it's not obvious that this would work. And if you combine the signals this way in the time domain, in the frequency domain, the Fourier transforms multiply. How cool is that? Okay? All right. And I think on that note of coolness, we will wrap it up for today. And then next time, I'll talk about some of the properties of convolution and why it is so important to your everyday lives. See you then.